Hello, my name is Yang Chen. I am a graduate student from South China University of Technology. Thanks for your interest in our work. I will introduce it in the following. Diffusion-based models, widely used in text-to-image generation, have proven effective in 2D representation learning. Recently, this framework has been extended to 3D self-supervised learning by constructing a conditional point generator for enhancing 3D representations. However, its performance remains constrained by the 3D diffusion model, which is trained on the available 3D datasets with limited size. We hypothesize that the robust capabilities of text-to-image diffusion models, particularly Stable Diffusion, SD, which is trained on large-scale datasets, can help overcome these limitations. To investigate this hypothesis, we propose Point SD, a framework that leverages the SD model for 3D self-supervised learning. Next, I will detail our method. Point SD adopts a two-stage training strategy to leverage the semantics encapsulated in the SD model to assist in point cloud pre-training. First, Point SD feeds noisy images rendered from point clouds into a frozen SD model and replaces the text encoder with a 3D encoder to obtain the 3D condition for denoising, thus establishing a point-to-image framework for subsequent feature alignment. Next, Point SD uses point clouds as the condition to extract features from the SD model and then aligns the output of the 3D backbone with them for pre-training. I will introduce the two stages separately. Previous method introduces an effective approach for utilizing diffusion models in 3D self-supervised learning by conditioning the denoising process on 3D features. However, the relatively small size of existing 3D datasets hinders the training of 3D diffusion models, which in turn limits the ability to learn robust 3D representations. SD, a text-to-image diffusion model, exhibits advanced representation capabilities and has been successfully applied to a range of downstream 2D understanding tasks. Owing to its proficiency in capturing rich semantic information in understanding tasks, we attempt to address data insufficiency using the SD model. In our approach, we train a 3D encoder to extract point cloud features and project them into a series of tokens. These tokens serve as the conditioning input for the SD model, replacing the text features typically provided by the clip text encoder to control image generation via the cross-attention mechanism. While this stage helps learn 3D representations, image denoising inevitably introduces low-level textures and details. These elements could distract the 3D encoder, causing it to focus on non-semantic features and hindering the learning of more robust 3D representations. To address this limitation, we propose a refinement that better leverages the semantic information encapsulated in the SD model, as detailed in the next page. We condition our trained point-to-image diffusion model on point clouds, allowing us to extract meaningful SD features for 3D representation learning. Compared to select features from the upsampling layers, our experiments show that features from the downsampling layers lead to better performance in 3D self-supervised learning. To leverage these features, we first project the point cloud representation RP from the 3D backbone F to the same feature space as the SD features using a projector. Then, we perform feature alignment via L2 loss. Such an alignment encourages the 3D backbone to learn more robust and meaningful features. During pre-training, we introduce an augmentation strategy to enhance 3D self-supervised learning. In the implementation, we first divide point clouds into patches and then mix them at the patch level. We build the augmented image samples by stitching two images along the width. With augmented input condition sample pairs, the 3D backbone will be forced to learn complex representations. We apply this augmentation strategy in both training stages. Here are our experimental results, showing that our method achieves competitive performance across multiple datasets. We also verify that the SD model shows a strong ability to distinguish features from different classes. In conclusion, this paper aims to harness the SD model for point cloud self-supervised learning. To achieve this, we propose Point SD, a point cloud pre-training framework that exploits the SD model's ability to enable a 3D backbone to learn representations with strong capacity. Experimental results on downstream tasks demonstrate that within our framework the SD model effectively helps the 3D backbone learn meaningful representations.